Good morning. Yeah, there we go. Need a little energy today. So today we are going to be talking about bias, specifically bias in machine learning. Show of hands, who is concerned about ethical development of AI? How do you feel about bias? Are we afraid of it? Do we see it as a challenge? Mixed reviews. Coming here to find out. Cool. Well, my name is Michelle Frost. I am a responsible AI consultant out of Accountable Intelligence. I'm also the tech advisor for the Ethical AI Council with the Center for Practical Bioethics. If you've seen my sidekick over here, his name is Wilbur. He is very cute and he will hopefully be quiet and not snore today. But in the event that my brain turns itself off and on again, he is here to assist me with that. So this is sometimes a little bit of a tough conversation, honestly. There's a lot of stuff to get through here. This is a really big subject, a really big field. And to be honest with you, I can't get through it all in an hour. So the approach, and actually we have 45 minutes down to 42, so it's going to be even less, and we're going to fly through a demo to prove some points here. So we're going to move quickly. What I want you to know is that this is going to be a wide yet shallow introduction to the topic of bias in AI systems, specifically in machine learning, and the introduction to the field of fairness and what that means. I'm going to go through some examples today that are real examples with real companies. You're going to know some of them. You could even work for them. And I leave the names in because a few things. Number one, if I redacted the names of the companies in these examples, then I'd lose your attention because you'd be trying to figure out who did this. And for the other reason is to prove a point that this can actually happen to any company if we're not paying attention, if we're not measuring different types of errors in our system. And maybe most importantly, and I'm going to stress this throughout the session, this is a socio-technical issue. What do I mean by that? I mean that the answer is not going to be in one single aspect. I'm going to show you a technical, okay, we're back, yes. I'm going to walk you through the technical perspective. How do we look at this from a mathematical angle? How do we look at this as technologists? But what you also have to understand is that the solution is not going to solely exist in technology. It's a social issue too. And so that's a pretty big thing. And we're going to get a little uncomfortable. I want us to think through this critically, not just as technologists, but also as humans. And so what the mindset I would like to start with is that this is a safe space, okay? If we can't have open conversations here in this room together, if we can't create a space for dialogue here, you're not going to be able to go out there and do it too. So knowing that we're going to get uncomfortable and talk about uncomfortable human things, if you are close to somebody that you haven't met yet, or maybe you have, just take 20 seconds here, introduce yourself to someone new. I'm serious about that. Okay. All right, come back to me. Save it for the coffee. So here's what we're going to go through today. Again, we're going to go kind of fast, but we're going to do a little bit of an exercise. And it's going to be slightly uncomfortable. We're not going to share things, but internally it might be uncomfortable. So that's why I wanted to warm up a little bit. Then we're going to talk about what is bias. What does that really mean? What does it mean in different contexts? And then how does harmful bias infiltrate AI systems? How has this bias actually caused harm? How do we measure it? How do we quantify it? How do we mitigate and manage it? And what I would like today is for each and every one of you to leave this room and feel empowered to participate in conversations and discussions around bias in AI systems. Okay, so here's a fun one. A very, very, very important thing that's noted on this slide. This is a wheel of privilege, intersectionality wheel of privilege, as observed in USA. I'm from the States, so culturally, contextually, this is going to differ a little bit. But a lot of times when we think of privilege, we might think of only one aspect. Maybe it's the color of our skin, maybe it's, education, wealth, status, all these different things, but there's actually a lot of different categories. And I'm going to read through different spaces of power, okay? The different categories and then what their power is. And mentally, what I would like you to do is just kind of take note. Do I fall into this space of power, this space of privilege? So just kind of check through this as I read through these different categories. So again, observed in the USA. Skin color, white, neurodiversity, neurotypical, mental health, stable, physical ability, able-bodied, religion, Christian, wealth, rich, age, adult, education, post-secondary, housing, homeowner, transportation, drives, political affiliation, Democrat or Republican, one of the primary parties, again, United States, marriage, monogamous marriage, citizenship, citizen, employment, salaried, language and communication, native English speaker, again, there's context here, sexuality, monogamous, heterosexual, gender, cisgender male, body size, slim and muscular. It's a lot of different spaces of power, right? And we don't call this out to bring shame to privilege. But what we need to do is recognize it. We need to recognize spaces of power that we occupy. Because if you have power in a category, you might have a privilege. And if you have a privilege, you might have a blind spot because you haven't experienced it from the other side. And if you have a blind spot, you have the potential to unknowingly leave space for a bias. So as I read through these sections, was anybody, just give me a show of hands, was anybody surprised by any of these categories? Did any of these come to you like, oh, I never thought about that before as a space of power? We're a very self-aware group today. Cool, I like that. Okay, so what's bias? Well, if we start with the big picture, right? The bottom of the iceberg, this is the frame. Societal bias, the systemic bias, right? This is the prejudices and stereotypes present within a society that can influence behaviors, attitudes, and decisions. They're reflected in institutional policies, social norms, cultural practices, okay? Wide scope. Let's go in a little bit narrower. Human bias, okay? The range of cognitive and emotional biases that affect individual judgment and decision making. These can come from a variety of things, upbringing, personal experiences, culture, and they're not all necessarily wrong, but we have to understand that they can lead to skewed perceptions. Okay? Start getting mathematical. Statistical bias, right? Technically, this is the systematic deviation of an estimator from the true value of the parameter that it estimates. It can come from flaws in data collection, processing, sample selection, statistical methodology. We're starting to get a little bit more technical here, right? Okay, well, what about AI systems bias? Well, we can also create AI in, we can create bias in non-AI technical systems too. So what about from UI development? What about the colors that we anticipate that our users could see? What about motion? I'm photosensitive. I have seizures sometimes. If I open up a web page and that thing is blinking at me, I hate it immediately. But then when we're talking about AI systems bias, right, this is unfair discrimination that gets embedded in AI models and in algorithms, okay? So often it's from skewed training, maybe flawed design processes, but it leads to unequal outcomes. And I want to drill in a little bit further, specifically when we're talking about the context of machine learning. This is an error that occurs in the model itself, and it's a result of assumptions that we make during the ML process. And this is kind of what we're going to dive into today. Where are the different spaces that we can inject bias in an ML system? Now, I have to call out that sometimes bias is necessary. So if you lose your keys, okay, and you're looking around the house for it, you probably have an assumption of where you might have left your keys. You're probably not going to go look in the refrigerator. Maybe you are, but you have an assumption, right? Okay? Otherwise, you'd be searching blind. Well, machine learning is much the same. It's a search process, okay? We need a set of assumptions in order to guide our search, otherwise we'd be blind. This set of assumptions is referred to as the inductive bias, okay? So the formal definition from Tom Mitchell is the set of assumptions that combine with the observed training examples deductively entail subsequent instance classifications made by the learner. Another thing I have to, again, address before we get into the meat of it, there's a trade-off, right? We've heard of overfitting and underfitting, okay? Bias, variance. We also need to talk about error. What is error? Well, mathematically, it's the bias, variance, and noise, right? Because we always have something that's a little unexpected, okay? So when we're talking about high bias, just if we're not familiar with this, we're talking about underfitting, okay? And high variance, we're overfitting. So models with high bias, they pay little attention to training data, and they oversimplify the model. Whereas variance, they pay a lot of attention to the training data, but then they don't generalize well when we put it into real production systems. Okay, so we've talked about the statistical things. What about harmful bias? How many of us are familiar with the machine learning lifecycle process? Okay, let's go through it. So this comes from a paper from 2020 called A Framework for Understanding Sources of Harm Throughout the Machine Learning Lifecycle, and we're going to use this as a guide today. I really love this paper. I think they did a fabulous job in trying to get people to understand how bias gets injected into systems. We're going to look at this in a couple different ways, but let's just go through so we can kind of simplify this down into two processes, right? So on the top bar, we have our data generation, okay? So we've got a world, right? We need to get data from it, okay? We select our data. We create populations. From those populations, we measure. Okay, and from that, we get a data set. And from our data set, we pre-process it, we split it into training and testing, and we evaluate it, we check out the benchmarks, how it's performing, okay? And then we start building our model. We take our training data, we decide how we're going to optimize it. We decide what our model definition is going to be. We're going to decide how we evaluate how the model is doing. What are we optimizing on? And then the model produces an output, and we look at that. Maybe we compare it to benchmarks, okay? And then it goes out into the world with real-world implications. And in this paper, they pointed out 7 different places of potential harm, potential bias that we could inject into a system. Now, we're going to go through these one by one, okay? So historical bias. We move into representation bias, into measurement bias, down here in our model building, learning bias, evaluation bias, aggregation bias, and then deployment bias. We're going to look at all of these and examples from them. But again, something that's really important here, that green arrow. What happens when we have a model that is producing predictions that affect people? It has real-world implications, right? So let's start out with historical bias. Garbage in, garbage out. We've heard of that, right? So even if you take data that's perfectly measured, it's perfectly sampled, we do everything right. If the world as it is or as it was contains prejudice, It's going to lead to a model that produces harmful outcomes if we don't take care of those, if we don't understand that we have this kind of data. This was an experiment that was done on ChatGPT by Dr. Hades Kotek and Dr. Ravit Dotan. They are absolutely fabulous AI ethicists. You can follow them on LinkedIn, and they've done some really wonderful experiments. But this was kind of early days of ChatGPT. And what they did was they took a different experiment, several different variations, and what they wanted to do was to get ChatGPT to say, perhaps a doctor could be a female, perhaps a nurse could be a male. And they took a sentence structure. The doctor yelled at the nurse because she was late. Who was late? According to the given sentence, the nurse was late, and the doctor yelled at her because of that. Okay, fine. We're assuming she, but the sentence is structured in such a way that this could make sense. They start swapping the nouns around. They start swapping the pronouns. They start restructuring the sentence to where grammatically it would not make sense for the doctor to be the male in the sentence. And yet, ChatGPT even goes so far to say in the given sentence it states the doctor was late, but it does not provide a clear reason why he yelled at the nurse. The sentence would make more sense if it said something like, the doctor yelled at the nurse because he was angry that she had not completed a task on time, or something similar. Like, it goes deep. And you can still do this, actually. Present day, ChatGPT, you can say, tell me a story about a doctor. It's going to tell you a story about a male. Tell me a story about a nurse. It's going to tell you a story about a female. Tell me a story about an engineer, male. Tell me a story about an engineer named Michelle. It's going to tell you a story that has something to do with the field of engineering and how it's not a female-dominated field. Same thing. Tell me a story about a nurse who is male. It will mention that despite being a woman-dominated field, there's a lot of different biases in ChatGPT. Some of them are maybe less harmful, in some ways, maybe amusing. If you start looking at different structural relations between different words, almost always you'll see the association between Russian and vodka. Why? Because it's in the training data. And yeah, we can giggle about it, but it is still a bias, isn't it? Representation bias. So what happens when a sample underrepresents some part of the population and it fails to generalize well for another subset? And this can be problematic if the target population doesn't reflect the use population, or if the target population contains underrepresented groups, or if the sample method from the target population is limited or uneven. Does anyone remember this one? It's 2015, I think. Yep, 2015. Android, Samsung, they started releasing this feature that automatically started cataloging what your photos were, and it immediately started tagging African Americans as gorillas. Does anyone know how they fixed it? They removed gorillas as a label. Why? They didn't have enough training data. They did not have enough representation of darker faces. Okay, so measurement bias. Features and labels are a proxy, right? They're a concrete measurement to represent a construct, an idea, or a concept. If we're building, let's say, some sort of classification method to predict what's in my hand, and we have different features and attributes about this water bottle. We can all agree that this is a water bottle, right? You might suspect, what's in the water bottle. It is water. But it's pretty concrete. What about creditworthiness? How do we define a system of measurement for ideas in society? So we're going to talk about this example quite a bit today. Has anybody heard of Compass? I'm going to maybe assume probably not. So this is in the United States. It's short for Correctional Offender Management Profiling for Alternative Sanctions. Okay, and this was developed by a company named North Point in the late 90s. And the idea was to predict recidivism. So recidivism is the likelihood that you have a defendant who has committed a crime. It's the likelihood that they're going to go on to commit another crime. And the idea was that they built the system in an effort to help judges determine if bail should be set. They had an intention with the system, right? This system went out, and it was at one point being used by 47 out of 50 states. Again, developed in the late 90s. It was not independently reviewed until 2017 by a journalism company called ProPublica. And what they found was, while on average between white and black defendants, the average accuracy was about the same, that was the average accuracy. And if you started digging into the different types of errors, so for black defendants, labeled higher risk but didn't go on to reoffend, false positive, 2 times more likely. Flip it for the white defendants, 2 times more likely to be classified as a false negative. So if you average those out, yeah, sure, they're about the same accuracy, but they fail in very different ways. Okay, aggregation bias. This is an assumption. This is the assumption that a one-size-fits-all model will assume mapping from inputs to labels and be consistent. Okay? But there could be underlying groups or types of examples that we should consider differently. This is an assumption that a data set might represent people or groups of people from across backgrounds or from cultures, and it's going to be the same. But we know that's not true, right? If I was building a text classification model, maybe we're trying to predict risky behavior, and I shot off a text that said, I'm going to be late, I'm on LSD. Flag? Has anyone ever been to Chicago? So I used to live in Chicago. LSD is Lakeshore Drive. You do not ever want to be driving on Lakeshore Drive, roughly 5 p.m., but we call it LSD too. So you might not be talking about drugs. We can't make assumptions, okay? Healthcare. So there was some studies done that there are hemoglobin markers that differ across ethnicities, okay? So if we make an assumption on one feature that it's going to perform the same, we're going to create unfairness in our accuracy of predicting diabetes. I'm going to start speeding through these because I'm talking slowly this morning. Learning bias. So this is when modeling choices may prioritize one objective which damages another. So, this is the objective function that a machine learning algorithm learns to optimize on. A lot of times, maybe we're looking at accuracy, right? But issues can arise if we prioritize an objective that damages another. Or maybe we want to, but we have to understand how these modeling choices affect our output. So for example, if we want to minimize cross-entropy loss for classification, that could lead to a model that has more false positives. What's the cost of a false positive in your application? Maybe the risk is low, so we actually did that intentionally. But if you don't understand those types of consequences, we can introduce bias. Now, this is one that's honestly hard to come up with an example because we would need open source models, but we can make some guesses, right? So one of the things that we'll talk about is that there is a trade-off. We talked about the bias-variance trade-off earlier. There's another trade-off between fairness and accuracy when you're looking at data that is historically biased. So Amazon a few years ago came out with a hiring tool, and immediately it was like, women don't work in tech, hire the men. It was addressed, it was brought up, I think this was 2018, wasn't that long ago. But we have to understand that the data that we're working with is biased. Okay, well what about when we start evaluating it? What happens if the benchmark data doesn't represent the use population? So a model is often optimized, right, on its training data, but the quality is measured on benchmarks. So this is a broader scale of bias. It's a misrepresentation benchmark that encourages the development and deployment of models that perform well only on a subset of the data that's represented by the benchmark. So There's a project that came out a few years ago called Project Gender Shades. If you go to their website, it's a beautiful UI. They've presented their study very well. Now, it's changed quite a bit. Okay. It's changed quite a bit, obviously, in terms of different accuracies, but at the time that the study was done, the top 3 facial recognition APIs came from Microsoft, Face++, and IBM. And, overall, again, average accuracy looks pretty good. But if you start digging into the different types of errors, there can be a big difference. So the biggest difference was 34.4% observed at IBM between a darker female and a lighter skinned male. That's a big difference in error. Okay, what about deployment bias? We built a model to solve one problem, but it's being used in another way. So this arises when there's a mismatch between the problem that the model is intended to solve and the way that it's actually used. Okay, so it's a framing trap, truly. Like if we build a tuna fish hook and somebody's using it to catch sharks, okay, that's a framing trap. If you build a model that's supposed to predict recidivism so that judges can use it to determine if they should sentence or if they should give bail, but then judges start using it for sentencing, that's a framing trap. But as technologists, as makers of these models, we have to understand how our technology could be misused. We have to understand this is how we intended it for, but could it be used in another way that would have negative consequences? I have some book recommendations at the end of this, and this is also included, but Virginia Eubank's Automating Inequality, it's a fabulous book. She has 3 different pretty big examples. But one of the ones that's really interesting is that there was a study done. They tried to build a model that would predict child abuse. But there's context to that, right? What if you can't afford to fix a window in your house and your child is cold? That might present itself in a model like this if they don't count for the nuances as child abuse. But that would look different in different families, right? So we have to understand the context of which the technology is operating within. We're here to talk about machine learning, but I also have to bring up bias in generative AI systems because it is also very much present. Another great example of a fabulous UI. I love a good UI. This was an article from Bloomberg that came out, I think, last year. Humans are biased, generative AI is even worse. And basically they did a study, give me a photograph of a politician. Give me a photograph of a fast food worker. Give me a photograph of a housekeeper. Give me a photograph of a criminal. And then what they did was they started looking at distributions, not only in skin tones, but also in gender. And they found a really big bias. And you can go there, you can dig into that. Again, we're not really here to talk about generative AI, but I am going to bring it up. Also, did anyone see this one earlier this year? Google Gemini? Yeah. Context matters. So some people said, actually I got a YouTube comment that was something along the lines of, I bet the folks at Google Gemini listen to the likes of her. And I was like, well, actually they didn't because that's still an error. We're here to mitigate errors, okay? We're here to reduce errors. This is an error. Why? Because we're not checking the output. Yeah, sure, you've made a fair model, but it's historically irrelevant. Okay, what are we going to do about it? Well, can't we just omit the protected attribute? This is a whole other talk itself that we are not going to get into, but the short answer is no, you cannot because of Simpson's paradox. And this is a statistical phenomenon that basically illustrates that trends that appear in different groups of data can basically disappear or reverse when the groups are combined. So in simple answers, basically the attributes the features are so tightly woven that even if you drop a column such as race, there might be other indicators within the data. And by removing that column, what you've actually done is removing your ability to measure it, removing your ability to mitigate it. And we're going to look into this in a demo that I'm going to go through very quickly. Okay, so measuring bias. So fairness. Fairness is an area of research in machine learning that studies how do we ensure that biases and model inaccuracies don't lead to models that treat individuals unfavorably. And also, I loved this because this is so true. Nobody gave a shit about fairness until like maybe 2015, 2016, and then everyone was like, oh God, what have we been doing? And now there's like a new paper on fairness coming out, I swear, every month, at least one, which is great. But it also shows the complexity of solving the issue, right? If we've heard of the statement, there's no free lunch, meaning there's not one algorithm to solve them all. There's no best model to use. There's no best algorithm. It's the same thing here. There's context. There's nuances. So what does it mean to build fair systems? When we talk about responsible AI, what's the difference between that and ethical AI versus equitable AI? Well, there's a lot of different answers here. The one that I will give you is when we talk about ethics, we're really talking about values, right? We're talking about beliefs. They could be for us as individuals. They might be in the company or the organization that we're operating within. Maybe they're in the industry that we're working within. Maybe they're on a larger scale and we're working against regulation. But they come down to values, okay? And what ethics does is it's a framework that allows us to take values and turn it into decision making, okay? And when we have made strategies for those decisions, and we start looking at values such as accountability, such as transparency, such as sustainability, fairness, we're making sure that systems are governed and that they're trustworthy. We're building responsible AI, okay? And when we're looking at equitable AI, we're trying to ensure that AI benefits everybody, right? That we treat everyone fairly, that we address issues like inclusion, like accessibility, like fair distribution of advantages. And there's a lot of nuances in here, right? We can go ground zero of we're going to just make sure bias doesn't exist, or we could innovate and say, well, maybe we actually want to generate equity. Maybe we want to help fix the system that we're working within against. Oh, and I'm going to keep flying through because I've got 10 minutes. Okay, so how do we measure it? As of right now, there are close to 30 different mathematical definitions of fairness. Shit, that's a lot, right? How do we choose which one? How do we know which definition of fairness we should use? Well, context matters. The answer is it depends. But I'm going to walk through a couple here just so you can kind of start getting an idea of how we start to look at these things, how we start to measure them mathematically. One of the most popular ones, statistical parity, also called demographic parity. This was created by Cynthia DeWerk. And it ensures that individuals from different groups have the same probability of receiving a positive outcome. Okay, so this is caring about the predictive equality, but not actually the ground truth. So we're not looking at what actually came out. We're just looking at if I take a male and a female and I want to see what their odds are of getting a loan approved, what are their odds of getting that positive outcome? Is it about equal? How do we look at that? So then we take this and we move into equal opportunity, which is very similar, except that we want to take that measurement of potential positive outcome, but we want to say qualified individuals. We want to define the attributes that would make someone qualified. And then we want to see across groups, well, how does this differ? And then we start getting more strict. Equalized odds. So this is an instantiation of the former of equal opportunity, but we start looking into the true positive rates, right, and the false positive rates, and we want to see that they are close to the same between different groups. Predictive parity, it's kind of on the same lines that we're looking at ensuring that the predictive positive outcome has the same precision across different groups, okay, but again, we're still dealing with positives. Now, one of my favorite things to look at is treatment equality. So how do we balance the ratio of false positive to false negatives across different groups? And I think that that creates, it might not be exactly what we want to use as the metric to go forward, but it helps us to create a holistic picture of how our model is actually performing. Understanding not just what our false positive ratio is across groups, but what's our false negative too? And the cost might be different depending on our application. So we're going to look today at a very quick example. I keep chit-chatting here, of pre-processing. And basically, this is mitigating bias through modifying the training data. So this might be via weights, via sampling methods, or transformations. But what I want to show you is that it does matter. How you sample matters. The types of underlying data before you train your models matters. In processing is actually where I believe we have the most room for improvement and where the research should be done. And this is where I'm focusing some research on here too, and is in the in processing. So these are techniques that modify the learning mechanisms or the algorithms to incorporate constraints or objectives directly during model training. So something that I work on is multi-objective optimization, meaning we were balancing, maybe we're optimizing on accuracy, but we also care about fairness, okay? And if these are dueling objectives, how do we find the middle ground? How do we find the model that seeks to balance competing objectives? And then there's also post-processing methods, and honestly, it's good if we're doing something, but I think that this is kind of the lazy approach, and this is basically at the end of it, we're like, yeah, we know our model is biased, we're going to alleviate, something so that we can say that we're taking action. It's kind of it's the lazy aspect, but it's still doing something. Okay, demo. Please be nice to me, computer, and I'm going to fly through this thing because I know I have 5 minutes. What I'm going to do actually, we've got 5 minutes. We can fly through this. Okay. So what I'm not going to show you is the pre-processing. Okay. Let's see what we can do here. Okay. Very quickly, I'm going to fly through this. So we talked earlier about that Compass system and the study that ProPublica did. Something that I have to note, so they published their data set, and the data set actually looks like this. So we have names of, okay, we're all struggle busing today. So we have the names of our defendants. This is going to be rough. What I might do is publish this on GitHub, and then that way you can look at it, because I feel like this is going to be a struggle, and then we're going to lose time for the rest of it. Okay, well, we're not going to look at the data set because we're going to try and speed through this. But basically, after we pre-process their data set, so something really important to recognize here is that this data set was an analysis, right? It was published so that we can look at it and we can analyze the different outcomes. And if you kind of dig into the representation here, so if we look at the distribution of race that Compass used, it's largely black population. That's the blue bar. So we're already starting out with an unequal distribution. And then you can start looking at things like distribution of the scores, okay? And you can look at the levels of prior counts. But bottom line is it's a very unbalanced data set. So it makes sense why we would have bias in an unbalanced data set that also operates in a system that already contains prejudice and bias. And what we can start doing, I'll publish this later today, and if I don't, someone yell at me on LinkedIn. But if we replicate the original ProPublica findings, we get in here and we get about the same average accuracy that they did, okay? And what we can start doing is we can start modeling the system. And if we model the system, we can get an average accuracy like between 74 and 78%, okay? But then we start looking at the false positive to false negative ratios, and we see very similar to what ProPublica reported. Okay. So this is from RAI widgets provided by Microsoft, and it's a tool that you can use locally in a Jupyter notebook that you can measure your fairness. So I send the model to it, I tell them what my protected attributes are, and I can say I want to see balanced accuracy. And from a fairness metric, let's go with the demographic parity difference. And instead of selection rate, I want to see the false positive to false negative rate. The orange is your false negative rate, and the blue is your false positive rate. So I think, looking at this, so I'm going to try and fly through here because I actually have 1 minute left. What we can start doing is we can start looking at different bias corrections. So through blindness, right? We talked about earlier, well, can I just remove the protected attribute? Can I just remove the race column? And when you do that, you find that it's literally the same ratio. It's the same thing. We proved Simpson's paradox. Okay, well, what if I start balancing the groups, okay? What if I say, give me the same proportion of black defendants as white defendants? Okay. It's still not great. Can anyone tell me why? I balanced the groups. Why am I still getting the same amount of bias? Why am I still seeing a big gap in our ratios of false positive rates to false negative rates? It doesn't matter if you equal out the groups if you don't also balance the target. We need in the training data the same number of positives and negatives in each group. So then actually, if you start balancing that target ratio, let's look at this again. So this is now with a balanced, another model. We've balanced the target ratio between each group. Demographic parity difference. They're almost equal. If you start digging into this, though, we did take a hit on accuracy. And that's where that fairness accuracy trade-off comes into play, because it's going to be really hard to convince a stakeholder that I'm going to take a 5% hit on accuracy for a small increase in fairness. And yet, that's what responsible AI is. That's understanding where we might have to make changes in order to continuously evolve and adapt our systems over time. And I am very quickly going to stop mirroring this. And run through the rest of this. Okay, so again, that's the technical approach. What's the socio-technical approach? Well, we need a lot of stakeholders, right? We need diverse groups and individuals with a vested interest in the development, deployment, and impact of these AI systems. We also need a human in the loop, okay? Until we can figure this out, we need the integration of human judgment and decision making. And then human-centered design. This is an ongoing and it's an iterative design process, okay? I will also quickly just mention, so there's a difference between reactive governance and proactive governance, okay? Those look very different in terms of strategy, in terms of how we organize and operate our products. Okay, so that looks like potentially, these are just a couple of examples. That's a very long list, but structured processes, SOPs. How do we manage the development, deployment, and release schedule of AI systems? How do we integrate our check and balances? How do we measure? How do we continuously monitor? AI systems are different than our web applications in that we don't just send them out into the world and say, see you in another 6 months or whenever there's a bug or a feature story. We gotta stay on top of it, right? It's a little bit more iterative. It's tighter feedback loops. And in those feedback loops, we have to create feedback channels. We need committees that need to be established and systems and mechanisms so that people can report in, and we create space for that. We all are familiar with the term of technical debt. What about ethical debt? How do we create space in our development process for understanding that there are going to be things that come up that we have to address? And that's a conversation about agile and product management, but I won't get into that segue today. What about through education? Okay, this is a complex socio-technical issue. Training and motivation need to come from a top-down approach. Okay, if we're developers, right, and we care about technical debt, if someone hasn't created space for us to address that technical debt, we're not going to stay up late into our evenings and try and manage that. Maybe we do, but if we haven't been given space to do the same thing here, we need that top-down approach. And yet, success is only going to be achieved if we have both top-down and bottom-up strategy in place. We need both sides of the party to care about the solution. I'll give a moment for, these are some of my favorite books. I have a lot more favorite books, but these are a really great place to start if you care about this problem space and if you'd like to learn more. And I will fly through this, but I also, like I mentioned earlier, tech advisor for the Center for Practical Bioethics, and we are helping specifically healthcare organizations approach ethical AI through a three-pronged approach through training, education, process improvement tooling, and executive level support. And if you'd like to get in touch with that team, here's a QR code here. And if you would like to connect with me, here is my LinkedIn here. And I know we flew through this. It's a lot of content to get through in even an hour, and it's a lot more content to try and get through in 45 minutes. But I think a takeaway that I would say is that fairness, it's not a byproduct of algorithms, okay? It's a deliberate choice. In some cases, it's actually taking a harder right over an easier wrong. But we have to care. And you can care because of your values and your ethics, or you can care because you want to mitigate risk, because you don't like lawsuits, or regulation says you have to. We can approach it from a lot of different ways, but our end goal is the same. And thank you all for coming, and I hope you have a good morning.